Hi class, welcome to the next section, chapter 3.2. Today we're going to talk about applications of the derivative. This probably doesn't mean what you think. In this context, we're not going to be necessarily covering word problems. We are a little bit, but more so we're going to talk about what the derivative means in general, because we didn't really talk about the derivative in the last section. We just talked about instantaneous rate of change. So today we're going to relate that to what the derivative is, and we are going to talk about how we can use the derivative to analyze our function a little bit, right? So that's more so what we're talking about as per applications of the derivative. As far as word problems are concerned and how it relates to the derivative, we will cover that throughout the course, and a couple of sections will be, in depth in that regards. So let's just kind of review what we talked about last time, because I feel like this idea of the derivative and the limit and the tangent line can be kind of overwhelming. So I like to go over it a few times in each section so that we're repeating the same information, right? So in the last section, we saw how we took a curve, in our case it was a parabola, and we took a secant line. And what we did was, a secant line intersects a curve in two spots. So we held one point fixed, and then we moved the other point closer and closer and closer towards our fixed point. And what happened was our secant line, whose slope is the average rate of change from one point to another point, turned into the tangent line, whose slope was our instantaneous rate of change. So it was a way for us to relate average rate of change to instant rate of change. Okay, so we took the secant line, we held one point fixed, the point that we're interested in, and we moved our second intersecting point towards our first, basically making that distance go to 0. In a series of images, it looks like this, right? So I have my point A, which I hold fixed, and this point Q will move closer and closer to P until it is at P. So you can see that the secant line here, the slope of this line is positive, more positive, more positive, and then the slope of the tangent line is even more positive, right? So we're looking at what's happening to the rate of change as our point Q moves closer and closer to P until it is at P. Okay, so this is rephrasing this. We're looking at this in a couple of ways, right? So first we looked at it as point B and its output, and then we kind of transformed the way that we look at it. Instead of looking at A and B, we looked at it as A and a point that is some distance away from A, right? So A, a distance of H away from my fixed point and its output, and they're identical views, right? If I'm looking at this in terms of average rate of change versus a difference quotient, it's really the same thing. It's just, am I talking about everything in terms of A, or am I now talking about things in terms of A and B, right? So we had kind of two different views for the same thing. So just to refresh, our instantaneous rate of change at some point x equals A is the limit as h goes to 0 of a function. In this case, I'm calling it s, of a plus h minus a being plugged into my function s over h. And I'll talk about why I'm choosing s in this section versus f, as I've been talking about it previously. A very minor reason, but it's the same thing. It's any function, basically, right? So the slope of a tangent line at a point is the following, right? So it's m, it's a slope, it's the instantaneous rate of change of my function, where I'm plugging in a plus h minus a over h and taking the limit as h goes to 0, right? So this is, again, the difference quotient. So both of these things are the same thing. Here, this function s can be the exact same function f. It doesn't matter. We're just using s because we're going to talk about a minor application. Well, it's not a minor application, but we're going to talk about an application of the instantaneous rate of change. And it's easier to talk about it as instantaneous rate of change than it is to talk about it as slope of the tangent line. So that's why we have s here. So this instantaneous rate of change at a point, this slope of a tangent line at a point, this rate of change of my function at a point has a common name, and that is the derivative. So all three of those things are the derivative of my function at the point x equals a. We denote the derivative as f prime of a. There are other notations for the derivative, but this is the most commonly used notation. This is, I don't know who made up this notation, but there's two different main notations because there are two different people who created calculus at the same time independently. Okay, one was Isaac Newton and one was Gottfried Leibniz. So we have two different notations because we had two different creators of calculus, right? So they were working independently in different countries, I believe, and they basically published their papers within a year of each other, but they were completely different works. So one had one approach towards calculus and the other had another approach towards calculus. So that's why we have different notations and different ideas and different ways that we kind of calculate things in this course. So the derivative of a function at a point x equals a is f prime of a, which equals the limit as h goes to 0 of the difference quotient. Okay. So the derivative at a point is the instantaneous rate of change of my function at that point. It is also the slope of the tangent line to my function at that point, and it is also the slope of the curve. Okay, you can think of the slope of the tangent line as the same thing as the slope of the curve or the rate of change of the curve at that point. So there's three different interpretations for it in terms of functions, right? In terms of functions. Now the application of that function means that the derivative has its own interpretation to that application, okay, which we'll go over in a little bit. One of those is velocity. That's one of the most common physics uses for the derivative is velocity. We know about velocity already just from everyday verbiage. Miles per hour, right? How fast you're going, kilometers per hour, depending on where in the world you are. Feet per second, meters per second, right? All of those things are how we talk about velocity. So the velocity is the rate at which something is traveling. Okay. Velocity has a direction, and it can be positive or it can be negative, right? So for instance, if I throw a ball in the air, depending on which way I'm considering to be up and down, there's a positive direction and a negative direction for its velocity. Okay. We also have speed, right? Speed is the magnitude of velocity. It's the amount of velocity that we have, right? This value is always positive or 0. So velocity has a direction, but its magnitude, the amount of velocity that we have, is always a positive value or is none. So whether we're going up or down, yes, there is an amount of velocity or speed, but the direction is how we quantify velocity. Okay. So example. Also, to preface this, generally when we talk about velocity, we talk about position as well. Position, velocity, and acceleration all go together, which we'll talk about in a little bit. And when we talk about position of an object over time, we generally use the function s of x or s of t. And so that is why we have this s function here for the instantaneous rate of change. Because when we talk about velocity problems, position problems, acceleration problems, it doesn't make a lot of sense for us to talk about the slope of the tangent line, but it does make sense for us to talk about how our situation is changing at a specific instant of time, right? How is my, in this case, as you saw, we're going to talk about a projectile. How is my projectile changing its velocity or its position or what have you, its acceleration at this specific moment in time? So, for example, we have a projectile. It can travel, a projectile travels up and then back down due to the force of gravity, right? So if you throw a rock, it goes up in the air and then it comes back down. Throw a ball, anything, right? So the velocity tells us its speed and whether or not it's traveling away from the Earth against gravity, or if it is coming towards the Earth with gravity, right? So for us, we're going to use a positive value as it's traveling away because the distance between the object and the Earth is growing, right? So we'll have a positive value. As it falls towards Earth, the distance between the object and the Earth itself is decreasing, so that's why we'll use a negative value for an object falling towards the Earth. Okay. So if we start to draw a picture, as I like to do when we have a word problem or application problem, here as our object travels upward, its velocity is increasing, right? Because its distance away from the Earth is getting larger, so it has a positive velocity. Here, it is at a standstill for just an instant, so it has a velocity of 0. So this is the moment when it goes from going up to coming down. It's not an interval of time, it is a instantaneous moment in time where it goes from going upwards to going downwards. So we say its velocity is 0 at that point, and after that, its velocity is then going negative. So notice that the speed is always positive, right? It's still traveling at a speed, and it's still traveling at a speed, but the velocity tells us whether or not the direction of that speed is positive or negative. So the projectile slows down as it reaches the highest point in its flight. Okay, so there is 0 velocity there. So for a single instant in time, it has a velocity of 0 just before it changes direction to go from positive to negative. Right? The speed throughout the entire flight is either positive or 0. It's the direction, right? Velocity tells us if it's going upwards or downwards, as well as its speed. Okay, so I mentioned this already. At the maximum, it was a velocity of 0. So this is an example of instantaneous velocity. Right? Instantaneous velocity, just at that moment, at that instant, what is its velocity, right? So our function is continuous, and it changes continuously over time, right? There's never a constant point, right? It's always curved. There's never a straight line anywhere in my function. It's always curve, all the way until it hits the ground again. So it is a continuous function, and our function is continuously changing. Okay, so it's easy to talk about how our function changes on average over time than at a specific instance, right? So when we have a position function, we generally call that position function s of t. Input is time. What we get out is its position, right? The average velocity from A to B is the average rate of change of my S function. So change in position over change in time is how I get velocity, miles per hour, right? I went from this mile to this mile over this many hours, right? So I would have miles on top, hours on bottom. That would be average velocity. So when we're driving our cars, that's why it's rated in miles per hour, kilometers per hour. Here's something like flight of a projectile, a ball being thrown, a rock being thrown, something like that. It would make sense to talk about feet over seconds, right? But it's a change in position. I went from this height to this height in this amount of time. So it's a velocity value that you're getting out. So this feet per second, this meters per second. Okay. Instantaneous velocity is the limit of this as h goes to 0. Remember, we replace b with a plus some value. So I'm interested in one point particularly, and I'm looking at what happens as I take that secant line down to the tangent line. So let's do an example. Okay, so let's say that a ball is thrown in the air, and its height in feet over time in seconds can be modeled by the following equation. Okay, so we have a parabola. You see it's concave down because it's negative, so it's facing downwards. And we have some shifts here, right? So we know where the vertex is. We know that it's been shifted to the left, to the right 4 units and up 6 units. So let's say that we want to know what the velocity is at exactly 2 seconds after it was thrown, okay? And 5 seconds as well. So what we do is we plug this in to our equation for instantaneous velocity, right? So at this exact instant of 2 seconds and 5 seconds, what is its velocity? So I take the limit as h goes to 0 of the position function where I plug in 2 plus h minus where I plug in 2 to my position function over h. So remember, this is really just average rate of change, right? As the distance between the 2 points gets smaller, one of those points being fixed. So when I plug this in, I plug in 2 plus h everywhere. So you see I have 2 plus h where t was, minus 4 squared plus 6 minus 1/2, all that kind of stuff. Then minus what happens when I plug in 2. So negative 1/2, 2 minus 4 squared plus 6. Notice I'm using parentheses because this subtraction here distributes across everything, right? So it's very easy that if I don't use parentheses, we've talked about this before, but if I don't use parentheses, it's very possible that most likely what would happen is that you get this plus 1/2 here. You distribute it here, but then people forget to distribute this negative to the 6 on the other side. It happens all the time. Very, very common mistake. So make sure you put things in parentheses, especially if you have some quantity minus another quantity where the things you're using have lots of arithmetic going on. Okay, so what we're going to do is we're going to simplify everything. This is obviously negative 2. We will square it. Here we will square all of these, but first we'll write it as h minus 2 because we have two constants here. Okay, so we're just going to simplify a little bit at a time. I'm sure you've noticed, but sometimes I go very, very slow, and sometimes I'll skip quite a few steps. Okay, so it really just depends on what we're doing at the moment. As we progress further in the course, I'll probably go a little bit slower because we have a lot of stuff that is going to be happening, right? So let's expand these things. So this is 1/2 times 4 minus 6. So that's really easy. Notice here that this plus 6 and this minus 6 instantly just drop off. So I can just disregard those and then just focus on this value right here, which turns into 2. And then this value right here, which I have to expand. Okay. So here I'm keeping those 6's, but again, notice that they will drop off. Here I have h minus 2 times h minus 2. This is not h squared minus 4. It does not work like that. Hopefully at this point you've gotten that misconception out of your system and you're taking this thing and you're multiplying it times itself twice. Okay. We're going to multiply this out. Perfect squares. So h squared minus 4x plus 4. These 6's will cancel. This will just be plus 2. I need to distribute this negative 1/2 across as well. Okay, so we'll take this slowly. Okay, here you see I finally dropped off the 6 and negative 6. Here I haven't distributed this negative 1/2 yet, so let's go ahead and do that. And then now you see here that I actually get this 2 and this negative 2 will also cancel. And so now I have a common h in every single term, which is nice because taking the limit as h goes to 0 with h in the denominator is not helpful. So it's nice that it ends up canceling everywhere. And I'm only left with one other h. Okay, so I have 1/2 h plus 2, which is continuous at 0. So when I plug in 0 here, I get that my limit is 2. So my exact rate of change, my instantaneous rate of change, 2 seconds after I've thrown this ball, is that my ball is still increasing. Okay, it's still going up because its rate of change is 2, has a velocity of 2. So it's still moving in the positive direction. Okay, so let's look at what's happening at t equals 5. I'm going to do the exact same thing. Plug in 5 everywhere. So 5 plus h and minus s of 5 over h as the limit of h goes to 0. Okay, so let's plug these values in. We got the same sort of situation here going on again. Notice that once I distribute this negative, the 6's will cancel out again. Okay, this is just a 1, so that just gives me 1/2 here. Expand this again after combining it, right? So I got to expand this as perfect square. So it'll be negative 1/2 times h squared plus 2h plus 1. Okay, here the 6's cancel. Now I can distribute this negative 1/2. Again, I have two constant terms that'll cancel out, and I'll be left with only h's. So I can cancel the common h that's everywhere. I'm continuous at h is 0, so I can just plug in h equals 0 here to evaluate this limit, and I get negative 1, which means that my rate of change at my instantaneous rate of change after 5 seconds is -1, which means that I'm decreasing in value. So at t equals 5, right, after 5 seconds, I'm now falling back towards the Earth. Okay. So again, notice that t equals 2 is on the left side of the axis of symmetry. So if we just look at our function here, I know that my axis of symmetry is at t equals 4. So here I'm looking on the left side when I should be, right, if this is my axis of symmetry, it's where the vertex is, right? So t equals 2 is on the positive side because the max is at 4, 6. So this line would be at 4. And then I looked at a point on the other side, which was 5. So it makes sense that when I plugged in 2, when I looked at the instantaneous velocity at t equals 2, it was positive, and for t equals 5, that it's negative, because I'm on different sides of the axis of symmetry. So one side I'm on the increasing portion, and on the other side I'm on the decreasing portion. Okay. When the ball is still climbing towards its maximum is when I'm at t equals 2. The instantaneous velocity, or the instantaneous rate of change, has a positive value. It makes sense, right? Similarly, when I'm at t equals 5, the ball is falling back towards the Earth, and I have an instantaneous rate of change of -1. So I'm decreasing. I'm falling at 1 foot per second in that case. Okay. Let's do one more example. So here, without looking at applications, we're just going to throw some math at it, right? So let's say, now that we have this notation, so say that the derivative at 5 equals 2. Okay, so the instantaneous rate of change at x equals 5 is a positive value. And when I plug in 5, I have an output of 10. It wants me to find the points A and B. So what I have is all the information for what's happening at 5. Okay, so at 5, I know I have an output of 10. And I know that the slope of this tangent line here, okay, is 2. This has a slope of 2. I also know that I have enough information to write the equation of the line, because I have the line's slope, because this is a tangent line. So at the point 5, I know that the tangent line has a slope of 2, instantaneous rate of change. Okay, it's the same as the slope of the tangent line. And I know that I have an output of 10. So I have a point and I have a slope, which means I can find the equation of a line. If I can find the equation of his line, then all I have to do is plug in 4.6 to get its output value, and plug in 5.2 into the equation of the tangent line to get its output value. So in order to solve this question, I have to find the equation of the tangent line first. Okay. So again, we know a point and the slope of the tangent line, so we can calculate the equation for the tangent line. So once we have that, then we can plug in our points, right? So I have y equals mx plus b. I'm going to use my point. 5 is my x, 10 is my y, 2 is my m. Okay, y equals mx plus b. Solve for b. Okay, this is going to be 10. Subtract it. B is going to be 0. Right, so the equation of my tangent line then is just y equals 2x. So to find a, I just plug in 4.6 into my tangent line to find its output, and I plug in 5.2 into my tangent line to find its output. So this is actually very nice and straightforward here.